If you look at a sperm whale, you aren't really looking at a whale. You are looking at a massive biological weapon attached to a tail. A full third of the animal's body length is just its head. And inside that head is a bizarre, oil-filled chamber so strange that when 18th century whalers first cut it open and saw the milky white fluid inside, they thought they were looking at the whale's reproductive organs. They were wrong. What they actually found was the most complex acoustic lens in the natural world. The sperm whale, Physeter macrocephalus, is the largest toothed predator on Earth. Adult males average 16 meters in length and 45 tons in weight. To contextualize that, the second largest toothed whale, Baird's beaked whale, reaches 13 meters and 14 tons. The sperm whale is in a different category entirely. But the most extraordinary thing about this animal isn't its size. It's a single anatomical structure that makes up a third of its body length, constitutes up to a quarter of its total mass, and serves three overlapping functions that no other piece of anatomy in the ocean can match. The sperm whale's head is simultaneously an acoustic weapon, a buoyancy engine, and a biological battering ram. And the story of how we figured that out begins with the world's most consequential misidentification. By 1712, Nantucket whalers had taken their first commercial sperm whale. For the men aboard those small vessels, the encounter with the head was unlike anything in their experience of the sea. They had harvested right whales, humpbacks, bowheads, animals with proportionate anatomy, blubber you could render into oil, a body that made sense in the way a large animal's body is supposed to make sense. The sperm whale didn't make sense. The head alone was bigger than their longboat. They cut into the dorsal surface of the forehead, expecting blubber, expecting the usual layered fat of a large cetacean, and instead, the blade opened a cavity filled with a warm, opalescent liquid that ran over their hands and soaked into the timbers. It smelled, according to William Davis's 1874 account, like raw milk. It was slightly viscous. It was unlike any blubber or oil they'd encountered. It was warm, body warm, and when they scooped it up in their buckets, it caught the light like the inside of an oyster shell. A whale produces something that looks like this from its head. The conclusion wasn't irrational. The conclusion was wrong, but it wasn't stupid. These were men whose frame of reference for biology was entirely practical. What you can harvest, what you can render, what you can sell. Whatever this was, it was clearly biological in origin and clearly different from everything else inside a whale. The crews called it sperma seti, medieval Latin for sperm of the whale. The word derives from the Latin sperma, meaning seed or semen, and seti, the genitive form of cetus, meaning whale, itself from the Greek ketos, meaning large sea creature. The Oxford English Dictionary records the English word spermaceti as early as 1471, which means the misidentification had embedded itself in the language before most of the men who perpetuated it were born. No single sailor made this mistake. The error spread culturally, across decades and multiple crews, gradually hardening into taxonomy. The whale itself was eventually named after the misidentification. The sperm whale is the spermaceti whale, shortened. Its scientific genus name, Physeter, comes from the Greek for blowpipe. Its specific epithet, macrocephalus, is Latinized Greek for big-headed. Every part of this animal's scientific identity, in other words, concerns its head. What those whalers were actually handling was a liquid wax ester. Not fat, not oil in any conventional triglyceride sense, not reproductive material. Spermaceti is chemically dominated by wax esters, primarily cetyl palmitate, which is hexadecanoic acid bonded to a long-chain fatty alcohol. The critical distinction. Fats and blubber oils are mostly triglycerides, where fatty acids bond to glycerol. Wax esters bond fatty acids to a fatty alcohol instead, producing a molecule with completely different thermal and physical properties. At sperm whale body temperature, roughly 37 degrees Celsius, spermaceti is a clear, watery fluid. Drop it below about 30 degrees and it begins to crystallize into a dense, brilliant white solid. It doesn't go rancid in storage, an unusual chemical stability for an animal-derived substance that made it exceptionally prized for long ocean voyages. At room temperature, it's a hard, oily-to-the-touch wax that is entirely devoid of taste or smell. The commercial consequences were enormous. The spermaceti organ, the whalers called it the case, could hold up to 2,000 liters of this substance in a large adult male. That's approximately 530 US gallons from a single animal. The harvesting process was labor-intensive and physically demanding in a way that defies easy summary. Once the whale was brought alongside the ship, the crew cut the head free from the body, a separate operation from the blubber stripping because the head was the prize. They would then open the case from above, cut a hole through the muscular envelope surrounding the organ, and lower a man inside. A boat steerer, usually, or an experienced hand, someone small enough to fit through the gap and strong enough to work in the confined space. He stood inside the open cavity of the whale's head, in warm wax up to his thighs, and bailed. Bucket after bucket passed up to the crew on deck, who poured the contents into casks for later processing. A large bull could yield 30 barrels, close to 1,000 gallons, of pure spermaceti from that single cavity alone, in addition to additional oil from the blubber and the junk structure beneath. Early 18th century records from the naturalist Paul Dudley describe yields of 20 to 50 barrels of oil per whale across the whole carcass. By the mid-1760s, spermaceti candle manufacturers had established themselves throughout New England. Spermaceti candles burned smokeless and brilliantly, with a high enough melting point that they didn't wilt in summer heat, and a quality of light that tallow candles couldn't approach. Candle power, the photometric unit formally adopted at the International Electrotechnical Conference of 1883, was defined as the light output of a single, pure spermaceti candle. The substance also lubricated precision clockwork, firearms, and watch mechanisms. It was used in cosmetics and pharmaceutical preparations as an emollient. Reportedly, it found its way into North American automatic transmission fluid, and due to its resistance to freezing in sub-zero temperatures, into applications where conventional lubricants failed. The machines of the Industrial Revolution ran partly on the contents of a whale's forehead, none of which brought anyone closer to understanding what that head was actually for. Below the spermaceti organ, in the lower region of the forehead, sat a second structure that whalers called the junk, so named because the oil they extracted from it was mixed with fibrous tissue and considered lower-grade material compared to the pure wax of the case. That dismissal turned out to be scientifically ironic. The junk isn't filler. It's, in terms of acoustic engineering, one of the most precisely structured tissues in the animal kingdom. To understand why requires opening the head and looking at what is actually there. The spermaceti organ occupies the dorsal, upper, compartment of the forehead. It runs the near full length of the nasal complex, from a structure near the blowhole at the front to the posterior end, where it terminates against the frontal air sac, a concave, air-filled reflector adhered directly to the trough of the skull. The organ is encased in a fibrous muscular envelope. Its cross-section is roughly circular, tapering toward the back. In large adult males, it extends approximately 5 meters from front to back. In a living animal at body temperature, it's filled with liquid spermaceti, the same warm, opalescent fluid those whalers stood inside on the open ocean. Malcolm R. Clark, the British marine biologist at the National Institute of Oceanography, spent the better part of a decade building the definitive anatomical picture of this organ. His 1978 paper in the Journal of the Marine Biological Association noted that the head, largely snout and the crest of skull necessary to support it, may exceed 1/3 of the total weight and 1/4 of the length of a large adult male. Clark measured the spermaceti organ's proportional size across individuals of different ages and sexes and found a consistent pattern. The organ is substantially larger relative to body size in adult males than in adult females. That observation, tucked into an anatomical description, would later become one of the central arguments for a function no one had seriously proposed in 1978. The junk sits below and in front of the spermaceti organ. Its architecture is entirely different. And this is the point where the head stops being a curiosity and starts being a machine. Rather than a single large sac, the junk is a highly compartmentalized structure, approximately 20 oil-filled compartments stacked in a layered series and separated from each other by thick transverse partitions of dense collagenous connective tissue. Each compartment holds spermaceti-rich oil. Each partition is stiff, fibrous, and acoustically distinct from the surrounding oil. The arrangement, as described in Clark's structural papers and later formalized in biomechanical analyses, consists of alternating compliant and rigid materials, a physical configuration that engineers specifically design into crash absorption structures and acoustic waveguides. If you had no idea what it was and you looked at it under a microscope, you would immediately recognize it as purpose-built for something involving energy management. The oil absorbs, the septa redirect. The geometry isn't random. The relevant Britannica anatomy entry states plainly, the junk of the sperm whale is the fatty structure found in the forehead of other toothed whales, known by whalers as the melon because of its pale yellow color and uniform consistency. Every other toothed whale, dolphins, orcas, beaked whales, has a melon, a fatty, lipid-rich structure used to focus echolocation clicks. The sperm whale has that structure. The junk is it. But the sperm whale then evolved an entirely separate, derived structure on top of it, the spermaceti organ, creating a two-stage acoustic system of a complexity found nowhere else in the ocean. Both structures ultimately serve the click. The click begins at a structure called the museau de singe, French for monkey muzzle, translated into English as monkey lips. Anatomically, this is the monkey lips dorsal bursae complex, positioned at the very front of the right nasal passage, close to the blowhole, just ventral to the anterior end of the spermaceti organ. The designation is significant. Sperm whales have only a single functional pair of phonic lips, the right side. The left phonic lip complex is vestigial and non-functional, reduced in evolutionary terms compared to the fully bilateral phonic lip pairs in dolphins. The sperm whale forces air through the right nasal passage. The monkey lips clap shut against the differential air pressure. That clap is the click, a single percussive mechanical event at the front of the nose. What follows is engineering that took decades to piece together. The initial pulse does not travel forward into the water. It travels rearward, back along the full length of the spermaceti organ toward the skull. The organ isn't simply a passive reservoir here. Sound moves through this structure quickly and efficiently, carrying the click pulse toward the posterior terminus of the organ. At the back end, the pulse strikes the frontal air sac, a concave, air-filled structure backed by the trough of the skull crest. The acoustic impedance difference between compressed air and soft tissue is enormous, roughly a factor of 3,000 in terms of specific acoustic impedance. The frontal sac reflects the incoming pulse back forward with high efficiency, the way a parabolic dish reflects radio waves. The sound now travels anteriorly, forward, through the junk's layered compartments and collagenous partitions, and exits through the flat, broad anterior face of the junk as a focused, highly directional beam of sound projected into the water ahead of the whale. This is the bent horn model, first proposed by Kenneth Norris and G.W. Harvey in a 1972 paper published as a NASA technical report, and named for its resemblance to a musical instrument in which sound is channeled rearward before redirection. The analogy used later by Bertel Mull was more specific, a bassoon. Sound goes in at one end, travels through a doubled-back internal passage, and exits in a focused form from the other. Bertel Mull, then at the University of Aarhus in Denmark, spent 2 decades extending and confirming the model experimentally. He was a meticulous acoustician, working at a time when the technology to properly measure the loudness and directionality of sperm whale clicks was only just reaching the necessary precision. But the decisive confirmation of the internal sound pathway came not from open water recordings of living whales. It came from a beach in Denmark in the middle of winter. A group of large adult male sperm whales stranded together in the shallow tidal flat of the Wadden Sea. Unusual in itself, since adult male sperm whales are mostly solitary, coming together only briefly and rarely. Stranded on the tidal flat, trapped by the ebb tide in water too shallow to maneuver. Mull's team received the alert and drove to the scene. By the time they arrived, one specimen, a bull of 15.1 meters total body length, was lying on its left side, semi-submerged, in approximately 2 meters of water. The only accessible part of the head was forward of the right eye. The team had about an hour from the last confirmed sign of life. They suited up and went to work. The equipment was improvised from what was available. A custom-built electrodynamic sound projector driven by hand-triggered pulses sweeping from 30 kHz down to 10 kHz across 25 milliseconds. A Brühl and Kjær hydrophone for receiving, connected to a DAT recorder. Both transducers were held by skin divers against the surface of the whale, handheld, in cold water, against the side of a dying 15-meter animal. The transmitter and receiver were placed at the frontal surface of the nose at 2 locations, the distal sac and the center of the junk. The session lasted 8 minutes. What they recorded in the autocorrelation functions of those signals was a repetitive, decaying pulse train with interpulse intervals of 7.7 milliseconds. From the known speed of sound in spermaceti oil measured by Fluellen and Morris in 1978, and the known dimensions of a 15-meter sperm whale's nose, the predicted two-way transit time through the spermaceti organ was approximately 7.5 milliseconds. The match was within the margin of positioning error for a handheld transducer placed against an animal lying in 2 meters of tidal water. Mull's 2001 paper in the Journal of Comparative Physiology stated the conclusion directly. The junk readily transmits sound and probably is in acoustic contact with the spermaceti organ. The multipulse pattern was reminiscent of the multipulse click peculiar to sperm whales. From the measured intervals, Gordon's allometric algorithm for estimating whale body length from click timing predicted a total body length of 15.3 meters. The measured length of the bull was 15.1 meters, a 2-centimeter discrepancy from a dead animal in the Wadden Sea with handheld hydrophones. The Römer experiment provided strong indirect evidence for the full acoustic pathway. The decisive bistatic confirmation came next. A recently expired sperm whale calf gave Mull's team the opportunity they needed. The Hawaiian Stranding Network retrieved the calf and moved it to a nearby laboratory facility where veterinary staff worked to keep it alive. Despite those efforts, the calf died. Approximately 20 minutes after death, Mull's team, now including Peter Madsen, Magnus Warburg, Whitlow Au, Paul Nachtigall, and Sam Ridgway of the Navy Marine Mammal Program, began the acoustic transmission study. The calf was floating in a temporary pool, 1.2 by 6 meters, filled with seawater. The head was barely submerged. The bistatic approach separated the transmitter from the receiver for the first time in this kind of experiment. While the Römer work had the transmitter and receiver essentially co-located, a monostatic configuration, the Kona experiment could place the projector at the distal sac and the receiving hydrophone at the junk, or vice versa, and actually trace sound transmission across the full anatomical pathway. The projector was a J9 transducer held against the skin of the calf's head. The receiver was a B&K 8103 hydrophone, placed approximately 16 centimeters away. They measured the signal at the junk when sound was projected from the distal sac area and at the distal sac when sound was projected from the junk. The key measurement, consistent across all recording configurations, was a reflection arriving 0.8 milliseconds after the initial transmitted pulse. Dissection of the calf's head had established the physical distance between the distal and frontal sacs as 55 centimeters. The speed of sound in spermaceti, known from Fluellen and Morris, is 1.37 meters per millisecond. Two-way travel across 55 centimeters, 0.8 milliseconds. The reflection at 0.8 milliseconds corresponded exactly to the frontal sac. Sound had traveled the full length of the spermaceti organ, reflected and returned. The paper's abstract described it clearly. The spermaceti organ and junk demonstrated an acoustic continuum. The 2002 Acoustics Research Letters Online paper's conclusion: sound is channeled rearwards in the spermaceti case from the monkey lips back toward the frontal sac, and there reflected forward through the junk. The bent horn pathway confirmed in an experimental setting for the first time, in a neonate, demonstrating that the acoustic architecture is present from birth. The acoustic properties of the spermaceti organ matter here in a precise way that extends beyond pathway conformation. The interval between successive pulses within a click encodes body length information. The two-way travel time through the nose is proportional to the length of the spermaceti organ, which is proportional to total body length. A listening hydrophone hundreds of meters from a sperm whale can calculate that whale's body length from the timing between successive pulses within a single click. This has been confirmed across field recordings from the Mediterranean, the Indian Ocean, and the North Atlantic. The output of this system, the focused click exiting the junk's anterior surface, has been measured at peak source levels reaching approximately 230 decibels, referenced to 1 micropascal at 1 meter, underwater. Context is essential here. Underwater acoustics use a reference pressure of 1 micropascal rather than the 20 micropascals used for in-air measurements, and the conversion between these standards involves a roughly 60 decibel offset from both the reference pressure difference and the acoustic impedance of water versus air. The 230 decibel figure isn't comparable to a 230 decibel in-air measurement. What is directly comparable is the relative statement confirmed across multiple peer-reviewed studies. Sperm whale clicks are by far the loudest sounds recorded from any biological source. Mill's 2000 paper in the Journal of the Acoustical Society of America measured on-axis source levels up to 223 decibels RMS. His 2003 JASA paper reported the single highest individual click measured at 230 decibels peak to peak. Zimmer and colleagues in 2005 modeled the P1 pulse source level at approximately 230 decibels peak at 1 meter, in good agreement with the empirical measurements. These are peak figures from the best studied individuals, measured with carefully calibrated large aperture hydrophone arrays. The beam directivity compounds the effective intensity. The same click measured on axis is 35 decibels louder than the same click measured at an oblique angle. The aperture created by the 0.8 meter frontal face of the junk in large adult males generates a narrow beam sonar capable of resolving prey targets at ranges of hundreds of meters in complete darkness. The whale produces several distinct click types depending on behavioral context. Standard echolocation, usual clicks, are produced in slow trains with intervals of roughly 0.5 to 2 seconds, designed for long-range detection during the descent phase of a foraging dive. As the whale closes on prey, the click rate increases dramatically and the pattern shifts to rapid, short-interval creak sequences. Social coda clicks, rhythmically patterned sequences used for inter-whale communication, are produced at far lower source levels, measured at roughly 161 decibels RMS, a fraction of the intensity of echolocation clicks. 3 different functional acoustic modes, all generated by the same 2 structures, controlled by changes in air pressure regulation at the monkey lips. One question about the hunting clicks has generated sustained scientific debate. In 1983, Norris and Merle asked whether sperm whale clicks might be intense enough at close range to acoustically stun or immobilize prey before physical contact. The indirect evidence invoked was dietary. Intact squid found in whale stomachs with no bite marks or visible struggle damage, suggesting capture without resistance from prey that should have been capable of vigorous evasion. The hypothesis was biologically plausible. The physics of the click, this close to the source, would impose enormous pressure on a small, soft-bodied cephalopod. In 2016, a paper published in Scientific Reports reported the results of actual in-situ observation of sperm whale hunting encounters. The finding was counterintuitive. Whales actively chased prey throughout the encounter, using echolocation continuously, and reduced the amplitude of their clicks by 20 to 40 decibels as the distance to the target closed. That's the opposite of the intensity burst a stunning strategy would require. The whales were turning down the volume as they got closer, not up. The acoustic incapacitation hypothesis remains biologically plausible in extreme close-range scenarios and hasn't been definitively ruled out. But it isn't supported as the standard mechanism. What the click unambiguously accomplishes is detection, tracking, and targeting of prey in an environment where no other sensory system functions reliably. The acoustic machinery alone would make the sperm whale's head the most sophisticated biological structure in the ocean. But marine biologists have identified two additional proposed functions for the same organ, each as counterintuitive as the acoustics. The first is buoyancy regulation. In 1970, Malcolm Clark published a brief paper in Nature proposing that the spermaceti organ might function as a biological ballast tank. 8 years later, he expanded this into 3 simultaneous papers in the Journal of the Marine Biological Association. One describing the organ's structure and proportions, one measuring the physical properties of spermaceti oil, and one presenting the full buoyancy hypothesis. The abstract of the buoyancy paper states, "Evidence is presented in support of the hypothesis that the whale can attain neutral buoyancy at depths greater than 200 meters by control of the temperature of the spermaceti oil in its head." The mechanism Clark proposed rests on a precisely measured physical property. Spermaceti oil changes density with temperature, substantially. Clark's 1978 measurements established the density at 0.853 kilograms per liter at 37 degrees Celsius, body temperature, rising to 0.925 kilograms per liter at 0 degrees Celsius. That's an 8.5% increase in density across the temperature range encountered during a deep dive. The theory is that the whale uses 2 complementary mechanisms. To sink, it draws cold seawater through its nasal passages, cooling the outer surface of the spermaceti organ and allowing the wax to solidify into a denser, heavier form. The increased density of the 2,000-liter organ tips the whale's overall buoyancy toward negative. It sinks passively, spending less muscular energy on the descent than it would otherwise. To ascend, warm arterial blood is routed through the vascular network surrounding the organ, melting the wax back toward liquid state, reducing the organ's density and restoring positive buoyancy for the return to the surface. The idea has been taken seriously enough to serve as the operational model for an autonomous underwater glider designed specifically to mimic sperm whale diving behavior, essentially engineering a submarine on the principle that if Clark is right, a fluid phase change system is an extremely efficient way to manage depth without continuous propulsion. But the hypothesis remains contested. No one has measured the temperature inside the spermaceti organ of a living whale during an actual dive. The thermal mass of 2,000 liters of wax is substantial. Cooling or warming that volume fast enough to generate meaningful buoyancy shifts within the time frame of a real dive profile is, thermodynamic critics argue, physiologically implausible. More recent research has questioned whether the biological infrastructure for Clark's proposed heat exchange, the specific vascular arrangements necessary to route seawater in the right direction at the right rate, actually exists in the configuration he assumed. Clark's 1970 and 1978 papers remain the standard reference on the hypothesis. It isn't disproven. It's unconfirmed and controversial, held in the literature as a valid functional hypothesis, pending evidence that has never arrived. What isn't in dispute? Sperm whales dive to confirmed depths of 2,250 meters, the third deepest confirmed dive by any mammal, exceeded only by the southern elephant seal and Cuvier's beaked whale. They remain submerged for up to 90 minutes per dive. They do this multiple times per day. Whatever mechanism manages buoyancy across that vertical range, a passive or semi-passive system would save enormous caloric expenditure relative to continuous active swimming. For an animal of 45 tons, that energetic difference isn't trivial. The second proposed secondary function is viscerally simpler to grasp, and it's the one that turned a biological hypothesis into a piece of maritime history. On November 20th, 1820, in the central South Pacific, roughly 2,000 miles from the nearest land, the sperm whale did something that no one who survived it could quite explain. The Essex was an 87-foot, 238-ton Nantucket whaler, built in 1799, commanded by Captain George Pollard, Jr., with first mate Owen Chase and a crew of 20 men. The ship had been at sea for over a year and was in productive hunting grounds when the incident began as a routine chase. A pod had been spotted. The crew lowered the whaleboats and went after them. Chase's published account, Narrative of the Most Extraordinary and Distressing Shipwreck of the Whale Ship Essex, written in 1821, describes what happened next, with a detail and clarity that reads like testimony, because it's testimony. The account of a man who watched from the deck as something went wrong that he didn't yet have a framework to comprehend. A large male broke from the pod. Rather than fleeing, it turned. It came toward the ship. It wasn't a collision of proximity, a panicked animal blundering into a hull in the confusion of a hunt. The whale was oriented toward the Essex, swimming directly at the bow, and it was building speed. Chase described it striking the ship with its head with a force that shuddered the timbers from bow to stern. The crew felt it as a jolt and then as spreading, grinding pressure, the sound of planking giving way under a load it had not been built to resist. The whale, which contemporary observers estimated at roughly 85 feet, though modern scientists consider that length significantly overstated, appeared to pause, lay stunned for a moment, then pulled away. Chase, still on deck, was processing what had just happened, what kind of damage they'd taken, whether they could pump out fast enough, when the whale came back. The second strike hit at greater speed. Owen Chase wrote that the whale had retreated about 300 yards and then turned and came at the ship with every indication of directed intent, accelerating through the water in a straight line aimed at the bow. The second impact opened the hull catastrophically. The Essex sank within approximately 15 minutes. 20 men escaped in 3 open whaleboats. They were adrift in the South Pacific, 2,000 miles from land, with minimal provisions. The ordeal lasted 90 days. Only a minority survived, and the manner of their survival, documented but left to other accounts, is one of the more disturbing episodes in the history of the sea. When Melville read Chase's narrative 3 decades later, it became the structural spine of Moby Dick. When marine biologists eventually read it, they began asking a different question. What kind of anatomy allows a whale to strike an 87-foot ship twice with its forehead and generate enough force to sink it? The answer came formally in 2002, when David R. Carrier and colleagues at the University of Utah published The Face That Sank the Essex in the Journal of Experimental Biology. Carrier proposed that the spermaceti organ and junk together function as a shock-absorbing battering ram, a structure capable of delivering catastrophic force to a target while redistributing peak compressive stress away from the attacking whale's brain and skull. The biomechanical logic is grounded in engineering principle. Large, fluid-filled cavities surrounded by compliant tissues absorb impact energy by redistributing force over a larger area and a longer time period, reducing the peak stress at any single anatomical point. The junk's layered architecture, alternating oil compartments and collagenous septa, is precisely the composite structure an engineer would design into a crash-absorbing system. The collagenous partitions experience tension during a posterior directed impact, the tension dispersing the energy of the strike laterally through the tissue rather than transmitting it as a concentrated spike to the skull. Carrier's 2002 paper identified a critical anatomical detail that Clark had noted but not fully interpreted. The spermaceti organ is proportionally larger in adult males than in adult females. The head is the most sexually dimorphic anatomical feature in a species where males already average 3 times the body mass of females. That pattern, disproportionate size in the one anatomical structure unique to this species, concentrated in the sex that competes for mates, is the signature of sexual selection. It's consistent with a structure under sustained evolutionary pressure from male-male competition, where the weapon and the shield are the same piece of anatomy. In 2016, Olga Panagiotopoulou led a team including Carrier to publish a finite element analysis of the sperm whale forehead in Peer J. The study modeled the head's internal architecture under simulated ramming loads. The simulation applied the load to both the anterior junk surface and, separately, to the spermaceti organ, to test which region serves as the primary impact absorber. The results showed that the connective tissue partitions within the junk significantly reduced von Mises stresses across the skull compared to models with those partitions removed or halved in number. When the load was applied to the spermaceti organ instead of the junk, skull stresses were lower, but the organ itself experienced high compressive stress that would risk damaging the acoustic structures housed inside it. The conclusion was that whales likely avoid direct impact on the spermaceti organ and instead absorb collision through the junk's anterior surface. This is precisely consistent with the observed scarring on mature males, dense, parallel, healed-over scar tissue concentrated at the rostral tip of the junk, not on the case above it. The wound record on the animals matches the predicted contact surface from a finite element model published 14 years after the original battering ram hypothesis. The behavior itself remained largely theoretical until drone technology caught up with the biology. In 2026, drone researchers captured the first confirmed video footage of sperm whales headbutting, footage that scientists directly linked to historical accounts of the Essex and to Carrier's mechanical hypothesis. A survey of tooth scars on male sperm whale heads found parallel scarring concentrated on 48 males, with the heaviest stage of scarring on animals over 43 feet in length, the largest, most combat-experienced males, carrying on their foreheads the accumulated record of a lifetime of head-on collisions that should, by every principle of blunt trauma biomechanics, have been fatal. The Anne Alexander, a second American whaling ship, was rammed and sunk by a sperm whale in August 1851, the same year Moby Dick was published. A 2017 paper in Aquatic Mammals documented a more recent collision between a research vessel and a sperm whale in 2007, in which video footage shows the whale swimming at least 150 meters toward the ship and increasing speed before impact. Behavior, the authors concluded, was unlikely to be accidental. Ramming isn't a historical curiosity limited to the 19th century. It's a documented behavior that the anatomy appears specifically evolved to support and that living animals still perform. 3 theories, 1 organ, 1 animal. The question of which function drove the initial evolution of the spermaceti complex is, at present, unresolvable, and the literature is honest about this. No peer-reviewed paper has declared a winner. No consensus exists. Hal Whitehead's comprehensive monograph, Sperm Whales, Social Evolution in the Ocean, frames the range of proposed functions as overlapping and possibly co-evolved, from Clark's buoyancy regulator to the battering ram to the acoustic focusing system. Timothy Cranford, writing in Marine Mammal Science in 1999, framed the whole nose as sexual selection on a grand scale, a phrase that encompasses both combat and acoustic signaling, since a male's click output is a direct physical signal of sonar system size, which is proportional to head size, which is proportional to body size, which is directly relevant in competitions for access to females. The fossil record suggests the organ is ancient. Liviaton melvillei, a raptorial sperm whale from the Miocene epoch, approximately 12 million years ago, discovered in coastal Peru, had a skull 3 meters long and very large upper and lower teeth adapted for active predation on large prey. The supracranial basin preserved in its skull indicates a substantial spermaceti organ was present. This fossil predates the modern Physeter macrocephalus lineage by millions of years, suggesting the organ emerged early in physeteroid evolution, before the deep-sea hunting ecology of modern sperm whales had fully differentiated, before the acoustic precision of the bent horn system had been refined to its current extreme. Something else drove the initial development. The selection pressures of deep diving and acoustic hunting subsequently shaped and enlarged it. Male competition may have run in parallel the entire time. These selective pressures can't be cleanly disentangled now, which may be the answer. They evolved together. They reinforced each other. The organ isn't optimized for one function. It's optimized for 3, simultaneously, because over millions of years, it turned out that those 3 pressures pointed in the same direction. Make the head bigger. The comparison to other large predators clarifies just how anomalous this evolutionary outcome is. Every other toothed whale, dolphins, orcas, beaked whales, porpoises, evolved a single forward-facing lipid structure in the forehead to handle acoustic output. The melon. It's a fatty, wax-rich tissue that focuses echolocation clicks and functions as an acoustic lens. Bottlenose dolphins have melons of a few kilograms. Orcas have larger ones, scaled to body size. The melon works remarkably well. It allows echolocation effective enough to hunt fish in murky coastal water, track conspecifics across kilometers of open ocean, and navigate complex 3-dimensional environments without visual input. A bottlenose dolphin's biosonar is one of the more impressive sensory systems in vertebrate biology. Peak measured source levels in dolphins and false killer whales reach roughly 216 to 230 decibels across the best performing individuals. But the dolphin's melon, at its most powerful, evolved for a hunting environment that is at most a few hundred meters deep, operating against prey that is relatively small and relatively slow. What the melon can't do is operate at 2,250 meters depth in 0 ambient light against prey as large and evasive as giant squid, with the acoustic precision required to distinguish a squid's body from rock and thermocline at ranges approaching half a kilometer. The sperm whale has that melon. It's called the junk, and sitting on top of it's a second, entirely derived structure, the spermaceti organ, that evolved in no other living cetacean lineage. The bent horn formed by the spermaceti case and the frontal sac reflector amplifies and refines the click in a way that no single forward-facing melon can replicate. The 0.8 meter aperture of the junk's anterior face in large adult males generates a beam directivity that produces 35 decibel differences between on-axis and off-axis measurements of the same click. That number, 35 decibels, represents a difference of more than 3,000 times in acoustic intensity between the beam's center and its edge. The system doesn't just produce loud sound, it produces specifically directed sound at a wavelength aperture combination that provides targeting precision far beyond what any other cetacean acoustic system achieves. Bertel Merle, summarizing the results of years of field measurements and cadaveric experiments, wrote what remains the most precise characterization of where the sperm whale sits relative to every other acoustic system in nature. No other odontocete produces clicks with this pattern, and no other odontocete has a structure comparable in size and organization with the spermaceti complex. The click generator, he noted, is by far the largest and most intense of all biological sound-generating mechanisms, specialized to emit the on-axis P1 pulse. The P1 pulse, the reflected, junk-focused primary emission. The click that has made the two-way trip through the bent horn pathway, reflected off the frontal sac and exited the forehead as the main sonar beam. Everything useful in the output has been through that full pathway. There are no shortcuts, and no other animal has built anything analogous. At 2,250 meters depth, the context for that system becomes absolute. Water pressure at that depth approaches 220 atmospheres, enough to compress the rib cage, enough that the sperm whale's ribs are bound to the spine by flexible cartilage rather than rigid attachments, allowing the thoracic cavity to partially collapse under pressure rather than fracturing. Ambient light is zero, not dim, not filtered, but zero, beyond the reach of any photon from the surface. Temperature approaches 0 degrees Celsius. The prey, primarily giant squid, can exceed 13 meters in length, have no interest in being located, and evolved alongside the whale in the same environment of total darkness. No visual system functions here. No olfactory system operates effectively at 220 atmospheres of pressure and 0 degrees Celsius. The only sensory modality that crosses these conditions reliably is sound. Specifically, a click generated at the monkey lips, driven rearward through 2,000 liters of liquid wax that is already beginning to cool toward its solidification threshold, reflected off a concave bone-backed air sac, driven forward through a stack of oil-filled compartments separated by stiff collagenous partitions, and projected ahead of the whale as a beam so precisely focused that it bounces off a squid's body at 300 meters and returns to the whale's lower jaw, which transmits the echo to the inner ear through a specialized acoustic fat channel in the jaw within milliseconds. The whale reads the echo, range, size, movement, another click, another echo. The transition from slow, usual click trains during the descent phase to rapid creak sequences during the final targeting approach mirrors the terminal buzz of an echo-locating bat in the last fraction of a second before catching an insect, a behavioral pattern confirmed across field recordings from northern Norway to the Azores to the Seychelles. The sperm whale isn't passively listening, it's actively steering by sound, adjusting click rate to refine range resolution, adjusting orientation to keep the beam centered on a target that is trying to escape, closing distance in complete darkness at depth that would kill an unprotected human in seconds. Bring the whale back to the surface, and the head that looms above the waterline looks, from any objective standpoint, like a mistake. It's a vertical wall of tissue, a block-shaped dome that makes the animal immediately recognizable at great distance, that creates drag, that adds tens of tons of mass the body must propel through water. Every other large predator in the ocean evolved speed, or teeth, or electrical sensing, or chemical tracking, or camouflage refined across millions of years of selection. This one evolved a wax organ, a 2,000-liter acoustic machine housed in a block-shaped skull, capable of being repurposed as a ballast system in the cold at depth or a battering ram during surface combat, depending on which evolutionary pressure was dominant in any given era of the animal's history. The men who named it after reproductive material they misidentified built an entire industry on harvesting it. They burned it in candles and lit the 19th century by it. They lubricated the precision machines of the industrial age with it. Candle power, the formal standard of photometric measurement, was defined by its combustion. None of them understood what it was for. The misidentification wasn't ignorance in the pejorative sense. It was the natural conclusion of encountering something genuinely unlike anything encountered before. A 2,000-liter sack of warm, milky wax inside the head of a whale looks, if you have no frame of biological reference, like almost nothing sensible evolution would produce. Even knowing what it is, Even understanding the bent horn model, the buoyancy hypothesis, the finite element analysis of the junk under simulated ramming loads, the structure retains a quality of impossible engineering. Every rule of marine predator design says an animal should evolve faster or stealthier or better armed. This one evolved weirder. And weirder turned out to be enough. The deep Pacific belongs to the sperm whale because the deep Pacific is dark, cold, pressurized, and navigable only by sound. The animal that evolved the best acoustic system owns that environment completely. The acoustic system lives in the head. The head is the anomaly. The anomaly is the advantage. It always was. Subscribe for more stories like this.